Hi everyone. My name is Wouter Krop, and I'm from the Flanders Marine Institute. And together with my colleagues, we made a model to do phytoplankton identification. So we've been collecting phytoplankton samples in the Belgian part of the North Sea since 2017. And then after we collect these samples, we put them through a high throughput imaging device called the FlowCam. We have version VLIZ4, and then we can analyze these images annually. We get around 300 to 400,000 images annually to be analyzed, and then we put them through a semi-automated pipeline. So we have a current working model to do phytoplankton identification. So then we get this unlabeled data and we start labeling them through the model, and then we check the results of the model to see if they are correct or not. So we get an extra validation, a human annotation, and then afterwards we have more validated data, partly through the model that has been conferred by the human, and then we have extra data which we can train new models upon, and we go through this cycle the whole time by creating more data with a better working model, and with this better working model validate more data, and then keep going through this loop. So then we have the most recent working model of this. We have this available in the iMagine marketplace, and to make it available for both experienced and non-experienced users, we can use this flowchart here. So we can either predict or train. So if you have the same classes, you're working in a similar environment as the Belgian part of the North Sea, you can just use our model and start predicting, and then you can manually validate if you want to. Or you have to train a new classifier because you have different classes, for example. And then depending if you have a server or not, you can either install it through GitHub if you have a server, and start doing this installation so you have it working in your own environment, in this own Docker container. Or you can call in on the iMagine marketplace, and then you can work from there, and we have some GPUs and CPUs available for you. So depending if you have coding experience, yes or no, you can either use the command line or use one of our notebooks. If not, you can also use our API, which has a more easy interpreter interface, which you can then use. And then based on this new model, you can do some predictions, or you through the notebooks again, or through the API. And of course, you can also turn this into another Oscar model, so you can do predictions in a more easy way. And this Oscar can be used through Python scripts or just through the website interface. So now we're going to go to our market architecture we've used. Then here on the right side, there's different buttons available. One important resource here is that I've linked our training datasets from Zenodo. So if you click on this, you will arrive on the training dataset that we used to train. And then I also made some user documentation available. So if you go here, you can see a new flow chart, which is specifically made for the marketplace. And then you can follow these steps because it will give you some information about how to make a deployment. And I'll follow them here. So if we want to do a simple deployment, we can just go here to deploy, and then we can choose this button. And then we arrive on a screen where there's two options. We can use DPass or Jupyter. So this DPass is the easy, simple to deploy for non-experienced coding users. So I'll call this demo API. And then you can put some description if you want to make it more clear. And the Docker tag, you can always use the latest one, or if you want to use a certain GPU or CPU. And I'll leave everything standard at 4 CPUs, but if you want, you can also get an extra GPU in there. But if you just want to do some predictions or simple prediction or simple training, we can leave this quite low. But it is thoroughly explained here how many you have to use depending on your goal. And then I'm also linked to our Nextcloud data storage. So I can access any data I upload on Nextcloud. And here I have an image dataset uploaded. And it's also explained on this page how to, of course, connect to this Nextcloud and upload your data there. So then I have my credentials filled in here. And then we can submit this one. So then this will create a simple API deployment, but we'll make an additional one as well that uses the Jupyter notebooks. So again, you can go to Phytoplankton Species Classifier, and you can either go through this button and then click Jupyter, or you can directly go here and click on Jupyter Lab. So I'll call this the demo Jupyter. You have to choose a password to log in on the Jupyter notebook later. And I'll leave the harder options again the same. And I again have storage. I again have access to the Nextcloud storage server. And also here you have an option, because we have this Zenodo training dataset. You can click on this, and then you will import our training dataset. For now, I'll just leave it be because I'm using a demo dataset. But if you can click on this, and then you can start retraining our model. So I'll submit this one too. So now there will be this one is just starting. And then when they are fully running, we can access them. In the meanwhile, I'll explain the other buttons you have available. So here we have the try. So then you can get a 10-minute short deployment to start testing it out. So this will load. And then on this first button, you also have the Oscar, which is like a serverless interference you can use. So then if you click on this, you can you can use Python scripts to do some predictions. And this is also explained on the Column Marketplace at the end under Oscar. You can do it through the site, which I'll explain after this, or you can use it through the Python script. So then if you want to do it through the site, which is a really user-friendly interface, you end up on this link. And then here I've made my Oscar deployment. So if we go to our phytoplankton classifier, we can upload any image here in the input. So we can select a file and then upload this. And then after a while, the prediction will appear in the output layer. So it will only take a couple of seconds, but then it will say something like this. It will say, I think it's this species, and I'm 99% sure, and these are the AFI IDs. So this is just a very simple version of our more complicated notebooks, but it's very user-friendly for somebody who doesn't have any coding experience. You can just upload their files here and then see the predictions. And the same can be done in the demo session after this is done loading. So now we have our two new ones uploaded here. So I'll first go to the API. So then this will load an API Swagger, and then we can train or predict. So again here, if you click on predict, try it out. You can upload a zip file of images, or you can upload just one image. And then you can do execute. And then it will say, I think it's this one, I'm 99% sure. So an important thing to notice about my model, it will always say the top 5 predictions, which I think it is, and it will say its confidence level. So you can see it's quite confident that it's this first one. And then we can also do training through this API. So here I have a link to the Nextcloud storage, and I have uploaded here an image file. So here, image mini version. Here I've uploaded around 50 folders, within every folder around 40 images. This is just a subsampling of our training data set, but here we have humanly annotated images, and then based on this, you can start training. So here I'll use everything standard, but you can change the batch size, learning rate, epochs, anything you want, the architecture. So for some people who know a bit of how models work, they can kind of fine tune or change the parameters based on this. If you want to change the split ratio, if you want to do more on training, no validation or something, you can change this. If you want to do some augmentation, this will be further explained in the notebook that I'll explain after this. So then we can just click on execute, and then this will start running. And then after a while, we can see after 15 epochs how far it got. So Apparently, I just got logged out. So here, if we go to our Jupyter deployments, these are the two I made yesterday just for testing. So these are the two new ones. You can go here and we use our password to log in. I tend to somehow always type it wrong on the first try. And then we will arrive under Jupyter Notebook space. We can see, I'm explaining a lot at the same time. I just want to show you that there's many different options to go about this, depending on your experiences or no. And so you can really use the flowchart on the GitHub to see which one of these you need at the end. Do you want to use the notebooks? Do you want to use command line within the notebooks? Do you want to use the API? Or do you just have to do some predictions through Oscar? So now I prefer this way of going about this because then you get access to the whole GitHub page with all the notebooks and everything inside. So there's two important folders here. One is here, the notebooks. I'll open all of them. And the second important folder for this tutorial is this one here, which is kind of, it's a config file to say, it's very similar to the one we saw shortly before in the API, but it's then here you can change the directory if you want, image size, number of classes. It's all the same things you can change, but then you can change them here manually. So I'll just run this script because this one can take a while to run the statistics. But now, if you want to start just exploring your data and go by it step by step, here I have either we can access our Nextcloud image folder, or I also have a small demo set here on the data folder. I have some demo images, which is a very extreme small subset with only like 6 classes and a couple of images just to really speed it up for this tutorial. So we can use the demo version and we can load the YAML file. And then this script is kind of saying the split you want to use because let's, for example, say you just upload some images, but you're not yet sure which part you want to use for training, testing, or validation, and you just want a random split. You can use this script and it will create a 0.7, 15, 15 split if you want to use both validation and testing in the YAML file. So then if we execute this, it will create here it will create some files which are just saying the location of the image and then the class it belongs to based on the classes that are put here. So this is just like an automation to create this split. And everything is again explained on the GitHub page to know how it should look like, the training testing if you want to make it yourself. If you don't want to do any random splits, you can follow this. So then we create a split, and now we can take a look at our distribution of classes. So here you can see a very small subset. We don't have that much triples, but there's a bigger distribution of the others. And then here by this random split, this is the total distribution, training distribution, testing, and validation. So it's just kind of showing some insight in how is the distribution of my classes. And then you can kind of look if they're equally distributed to say like, oh, do I need to use class weights if they're fairly imbalanced, or can just use it normal? It can give you some insight in the parameters you can change in the config file or in the API file. Then we can take a look at the width and the height of our images by making this histogram, and then we can kind of see, because we rescale the images to be put into a model to see, we rescale to 100 if this makes sense. If you have different sizes of your images, you can change this. But this notebook is just kind of an exploration of your data set. How does it look like? What is the average and everything? So here, then we can go, there's an additional optional file if you want to do data transformation. This is, for example, if you have a different FlowCam, you have one with colors, and you want to go to an image that would match best with our data set. I've made some simple scripts to go from colorful to grayscale, which are similar to our images, so you can start training with these classes. But of course, it really depends. You have to kind of fine tune it to make it match, because this one is too bright, but for this one it works. So it depends on your data set, how you want to change your images to make it look like our images if you have a different FlowCam. This notebook is then about the augmentation. So again, I'll load the demo file and the split script. And then here, if you want to do any augmentation, for example, your data set is not big enough, or if you want to see if your model can pick up on some things, you can flip, rotate, crop, zoom, blur. There's a lot of different options here, which are explained, that your original images get like changed a bit, and you can put this as input into your model, so your model is able to pick up on different variations of your image. So you can choose if you want to turn this on or not, and to which extent you want to use these parameters. And of course, this is again linked to the config file. So if you go to the bottom, you can change all these parameters and you can turn them on, yes or no. I've put them to false because my data set is big enough, but if you want to kind of play with this, you have the possibility. And then here we have the training notebook. But now to make it simple, because we don't have time for a full training, I'll put epochs to 3. And then when we load the script, so we just have 3 epochs here. And then we can start training, and hopefully by the end of my talk, I will show a simple version of these 3 epochs. So it's loading the whole model. So then, so this is again training. This one is training on our Nextcloud image folder. So this is subset. So it's a bit bigger than a demo set, which just has 5 classes, but it will still take some time to go through all the images. And then after your model is done training, you can do some predictions and to see how the model is performing. So now I have this linked to our best working model from VLIZ. So we have the notebook folder, we have this folder which is the config files, and then we can go to models. And here we have the VLIZ existing model, which is our best working model. Then you can use to do some predictions, or if you want to change a bit. And then this one is the new, it's with the current timestamp, it's the one with the 3 epochs that is currently being trained. So then in this VLIZ model, we can load this one, and then we can do some predictions again on our demo files. So this script is just again splitting, saying if the data has not been split yet, it will split it. Otherwise, it will just load the dataset files or prediction file. It will predict on this, and then it will create a JSON file. So YAML. Now it's predicting just on these 8 files, and then we can take a look at the predictions. And here we can see this one we just made. So it's loading the test file, which is showing the location of our images. And then it's saying the predictions it made for every one of these files. So the top 5 predictions I think it is. And then the probabilities along with these predictions. So it's 98% sure it's this class, which actually also matches with our file. But we'll have a better script to really look at how performant it is. But it's important to know we always get the 5 top classes with the confidence level. So then we can predict our test file, or we can just predict one single image where we have the location of. We can say, hey, predict this one. And it will say, I'm 99% sure it's triples. Or we can say, hey, predict all the images within this folder. So you can upload your data here by just uploading it, or you can link it to the Nextcloud server. And then you can say, hey, predict everything within here, and it will give the prediction and the confidence level. Or you can say, hey, I have this folder. I have different observations of the same cell I took pictures of, the same bacteria, of the same phytoplankton. And they're from different angles. I want to say, hey, for this folder, I want to predict what is the final results by looking at all the images. What is this species I just looked at? So this has, for example, 3 pictures of the same sample you took, and then it will say, hey, for this folder, I'm 99% sure it's triples. The same can be done for online images. You can link to these, but of course, they don't really have the exact same layout as our images. This is just a random link to an online image, and it has some text on here. But it can work on online images, and they can do a list of online images, or they can again do the same observation from different perspectives and say, hey, for all of these pictures of the same observation, which one do you think it is? But I recommend using just this split script if you're doing a fully training, or just locate an image folder and predict all images within this folder. So then we can go to our prediction statistics. So then this is kind of looking, because we have humanly annotated images, we want to compare it to the prediction of our model. So we want to see if the prediction of our model matches with what is the ground truth. So we load our best working model. We kind of make the JSON file that we've created make sense. And then we can look at the statistics a bit. So here it's saying the top one accuracy is around 85%. So it's the class which is most confident about. The first one is 85% correct. But if you look at if the true label is in the top 5 classes, it is 98% of the times it's in there. And I think the top 3 is something from 97. So it's quite performant. It's not always the first class, but it is. If it's not the first one, it will be the second or the third. So then here you have some extra precision and recall metrics. And then I've made some plots, like for example, the confusion matrix. So here we can go to results, and this plotted the confusion matrix in this folder. So I have made the normal confusion matrix, and I've also made a weighted one. And for this normal and weighted one, for both of them, I've made a filter depending how confident we are about the data. So this is just the normal confusion matrix, no filters, just one-on-one coding. Is our most confident prediction, is it the same as a true label? And you can see we get a very nice diagonal. But if we put a filter by saying, hey, let's only show the data where we're at least 75% confident. So where data where we're kind of split in between 2 classes or 3, or then we remove those data, or we don't show them in the confusion matrix, you can see that some of the misclassifications get filtered out because I wasn't so confident about them, and at the end they weren't right. So here we get our confusion matrix with a little bit better performance. And then I made an extra plot here in the cutoff ranges. So here, this is a figure that is kind of saying, if we increase this filter, if we apply a filter to our predictions and say, hey, let's not look at all the data has been predicted, but let's just look at the first class which is predicted, and let's say you have to be at least 80% confident about this class. Otherwise, we won't look at the prediction you made. So here you can see, of course, if you don't put any filter, we get 100% of the data, which is this red curve. But if you apply a filter and say you have to be at least 80% confident, we do get 10% of the data removed, because you have to look at this red curve here. So 10% difference between the full. But the higher threshold you put, so the more strict you are about how confident your model needs to be, the better performance you also get. So you get a higher accuracy, you get a lower false negative rate, but you do lose data. And this makes sense. The more stricter you are about how good the model should be, the less data will be left. You only lose here for about 99% confidence, you only remove 70% of the data, but you do get very high performance. So this is just showing this for one class, but we've also made this figure in general for the whole, for all of the images. And again, you can see if we look at an 80% threshold, so we need at least 80% confidence, we lose 10% of our data, which is now this purple curve, but we do get a little bit of higher performance. And if we keep following this threshold curve and we keep going to the right, we can see we get more and more correct. Our model is more and more correct because I was more confident, but we do lose data where we are not confident about. But then you can also look at this case by case. For example, here, so I've just learned this whole notebook, but it just basically makes all these figures. We can look at apicundularia here. So this is showing for, again, if you look at the 80% confidence, so it's two different figures. One is the proportional progression, the other is the absolute progression. So if you look at, you have to be at least 80% confident, then you create some white space here because this data is filtered out. So from the total amount of classes with 33 or something, you at the end get only 30 at 80% confidence. But you can see proportionally, the blue one, which is our correct class, gets bigger and bigger in proportion. And at the end, at 99% confidence, we do lose some data, but all the data we have left is this right class. So you can look at this on the left as well. You can see proportionally, the higher we put our cutoff ratio, the higher we put our filter, then the less data we have left. Yes, we get some data moved out, but the data we do have left is our correct class. And then this is done for apicundularia, but then if you look at this class, for example, here it kind of stays the same the whole time. So like you can increase the cutoff ratio, but you don't really get an extra performance. It kind of remains the same proportionally. You get a very small peak over here, but then to say to the user and say like, hey, you can, for example, say to the user, hey, if you're fine with 98% performance, you can just, for this class, if the model predicts this class, you don't even have to validate anymore. You can just say, hey, it's correct. We can validate the others. This seems good enough. So it depends on your call. So if you look at this class, here, it doesn't really make sense to apply a filter because if you increase the cutoff ratio, you remove, of course, data, but the most data is removed is also from the right class. So it doesn't really make sense to say like, hey, let's from an 80% confidence, we can say to the user, we don't have to validate anymore because here, every data, almost at every cutoff ratio, it remains the same performance. It remains 75% correct, and it even decreases with the higher cutoff ratio. And I'll take a look at maybe this one. So here you can kind of say if you want to the user, or the user can decide for himself and look at this graph and be like, okay, if we increase the cutoff ratio, we do get a higher performance. We almost get 100%. I think there's only a few misclassifications, but you can say for this 99% filter that we don't lose that much data, but the data that we do lose is the one from the misclassifications. So you can say, hey, for this class, if the model is 99% correct, you don't even have to look at it anymore. It's correct. And if it's below it, you can maybe check. So it really can be a case-by-case comparison where you go through all these images and then say like, for this class, if you're fine with 99% accuracy, you can just leave it be. If you want to, and here, like I mentioned before, you can put it at 90% and be like, hey, I lose this amount of data. So for this data, I approve. I say 90% correct, the data that is correct here. I will look at it. And for the remaining data where the confidence is less than 90%, I'll take a look at it and it will be this part of the data. And then you can see, hey, here, this is wrong, this is wrong, this is wrong, this is right. So it kind of speeds up the process of the human annotator. Instead of looking at all the predictions that the model made to create a bigger model, you can, depending on the class, say, hey, from 90%, from 70%, from 100%, this data is good enough. And we'll take a look at the data we're less confident about and then see if there's been misclassifications here so we can retain a model in a better way. So I'll close all of these. And then we have the model is still training, I assume. So here is, it's done. So now we have created, here we have created a new model file, and then we can do the same thing for the predictions for this new short model, but then we kind of have to say the location of this model. We can say, you have to say this timestamp instead of the phytoplankton VLIZ, and the same thing can be done And we can also look at the performance. So here we'll have a monitor option. And then while it's training, you can take a look at this and you can see how, because it only did 3 epochs, how the accuracy is increasing. And the same can be done here for our demo version. You can take a look at the monitor. And then this has 15 epochs, so I assume it's still running. So yeah, it's here in the 6th epoch, and you can see the accuracy is increasing while we go along. So I've explained the Oscar, which is show the output. I'll see here on the marketplace if the demo version is just another alternative. I only have 10 minutes of time to use this. It's just a quick example, but now I spent more than 10 minutes showing the notebook, so it'll take some time to load again. But I just want you to be aware that we have many different options of predicting. We can use the notebooks. We can use command line within the notebooks. So I didn't really show this, but the notebook of prediction is basically saying, of training, sorry, is basically saying, hey, run this file within the Plankton class. Because here in the Plankton class, we have all our training files. You can just command line this and say, hey, run this file. If you prefer that than using the notebooks. Or you can use the API, which is more user-friendly. So I think now I explained most of the information about our classifier. I've explained where to find our data sets, the documentation. You can use GitHub if you want to run it on your own resources, and everything is explained here, how to install it locally or Docker, how to make your data fit, how to use the notebooks. And you can combine the API within the notebooks. You can do many different things. And yeah, here the timing is done now. So here you can just upload an image. It's kind of similar to the Oscar. Okay, I have to select. So this image, you can just say submit. And after a couple of seconds, you get, it's this class, and I'm again 99% confident. So it's kind of showing what is possible. And then you can choose to use Oscar. If you want, you can choose Oscar in the URL. If you want to do predictions, you can use Oscar through Python scripts. You can train within the notebooks. You can train through the API. You can train on your own resources. You can do a call-in. There's many different options. I hope I explained it quite well. I can go deeper if there are any questions if I went too fast over some of these notebooks. But let me know if you have any questions.
Thanks, Wout. So we do have a question. I'm not sure you can see the Q&A chat. Otherwise, I will read it for you.
I'll open it. How do you pick a correct prediction of the 5? So the correct prediction can, if you are working with validated data, you can, because we have our data folders on Nextcloud, we know what, because we have a human that has already annotated these, we have our trained data set with labeled images. We can look at the prediction which the model made and then say, so here I'll go to models, predictions. So we can look at the predictions that the model made and the confidence it has. And then we can look at the true labels, because we do know at the end, we have labeled images what it is. So we then have to look if they match or not. And then through these notebooks, you can see if the first one matches, or if it's not in there, if the model was wrong. So you have to manually see if the model is correct through these notebooks. And then the predicted data, for non-annotated data, you only get the confidence of the model. So you do need, you have to check yourself if the model is correct. You know, by with a certain confidence, you can say for some of these, like I shown in the images, you know results. You can see, for example, for this class, if you have the same training, you can assume that it's right because for all our training data, it has always been right. It's always been right 99% of the time. But of course, if you want to go check if it's right, you need somebody who notified the plankton species and then confirm. For all of these, you can see it's confirmed, so it should be the same. But for non-annotated data, you can see how confident the model is. And this confidence should say something about the accuracy, but of course, it's not a one-on-one relationship. I hope that explains your question. You do need at the end a human to interfere for classes which the model is not confident about. If the model is confident, you can kind of trust it. Okay, thank you.
And there's a question in the chat about how do you do the quality control?
So the quality control of the model, I haven't seen the chat yet. How you do the quality control? So we check here in the statistics to see if at the end for our test data set, if the model is performance. So it can be for the training, it's really good, but you always have to have an independent test data set. And we just made the split. We went over our training data set is around 95% has 95 classes. And we have explained it here about the coordinates and everything. So, and then we have just a random split going around all these classes and making 10% of all the data, independent. And then for this independent data, we can then see if the true label that we have or ground truth matches with the most confident prediction, or if it's not the most confident, the second or the third, and to see how good the model is performing.
There is a specification or refinement, so the quality control of the right image classification.
I'm not sure if I fully understood the question. Quality control of the right image classification.
So let's see if we can have further details. So maybe you answered it correctly.
Yeah, if you Stella Berger, you can always reach out to me through email, or you can put your question more thoroughly in the chat if it's possible. But like I said, it's you check if you trust the class based on the general performance of the class. You can say it's 99% correct all the time. I don't want to check it, but if you do want to check everything, you can go by it manually. Can a human see the images for quality control? So afterwards, you can of course just look at the images. You have the prediction file here, which says for this location of the image, I have this class. But then you go through these notebooks. You cannot see directly. I've not made a notebook yet to show like this is the image and these are the 5 predictions. It's just shown here with the location and the image which you think it is. But of course you can export this JSON file and then have one big CSV file saying the location and the top 5 classes, but it's not yet. There's no real labeling, yes or no, correct API or something like that.
Okay, so before going further into the chat, there are 2 questions in the Q&A part. 2 more. So.
Could you also say something about data compiling? You have images and depiction JSON files. How do you put them together? For example, the abundance in your sample. I've not made a notebook about this. The notebooks are just about doing the predictions. But then to look at the specific sample and say it's 80%, like what the distribution of the classes is within that sample. At the end, you kind of have to do yourself because the model says which classes it thinks it is there, but then you can just export the JSON file and then look at it yourself at the top 1 class and the distribution of this. And then Tom, hi Tom. Thank you for the great presentation. Have you looked at the ability of the model to work with non-FlowCam images? Are there any plans to look at this? So we've been looking at new FlowCam versions. That's why I made the transformation script. And we have ordered a new one at FlowCam, and we're just starting to create samples. So as soon as if you have a big enough data set, I would like to train a new model with the colorful FlowCam trained and use the kind of the weights of our use the weights of our of our gray trainer, and then create a bigger data set, and then at the end make a new classifier for this new FlowCam by expanding the data set. But I've not through this platform I've not looked at any other non-FlowCam images.
Thanks, Wout. And then there's one question back in the chat from from Jens.
How do you pick out only the uncertain ones, the human interference, how to look at images to inspect the not sure images? How do you look back for every image? So you there's not been a notebook of this yet, but if you have the JSON file with the confidence ratios, if you export this and you can just put you can create, maybe you can just put the image and then the confidence rate and then the confidence ratio and its top prediction. You kind of have to do this yourself. Within VLIZ, we have our own labeling. So we do this. We have our own working tool to validate the predictions we've made. And then we can say, hey, this is what the model says. And we can say yes or no if it's true or not, or we can re-change the label. So we kind of have our own kind of home working tool. But it's a very simple one we made, and it's only working in-house at the moment. But you kind of have to make something for yourself to go through the predictions and see how if the confidence ratio matches also for your images. I think this tool is only working in-house. I'm not sure if you have a plan to publish this because it's linked to our MongoDB database, and it's only working one way for us. So my apologies, but I don't think this will be published. But I think it's you can make something similar, like I mentioned before, to show the image and show the label and to save yourself yes or no.
Okay, thanks a lot. And there's one more question.
Yeah. Do you have a tool for biomass volume estimation calculation included already? So no, we don't have a tool to do this. The tool, we just have something to go from image to the prediction, but nothing yet sample based. You can put specific samples in there and look at the classes, but we don't have any estimations about the biomass or anything like that.